Hi, my name is Grace Campbell with the Kentucky Mesonet at WKU, and my project, in conjunction with atmospheric scientist Dr. Eric Rappin, is nocturnal thermal inversions in Kentucky's water-rich climate. Nocturnal temperature inversions occur after the sun sets here in the bottommost 100 meters of the atmosphere. It happens when the bottom layer here cools a lot more rapidly than the air above. And so what happens is we end up with the coldest and densest air here at the bottom, and the warmer, less dense air ends up at the top of the atmosphere. And that can create a lot of issues because this is a very stable environment. And so the air does not want to mix because, quite frankly, it just doesn't want to. It's in a stable situation that it just wants to stay in. And so this can cause a lot of issues across many sectors across Kentucky. A big one that we're having recently is in agriculture. So whenever farmers spray their fields, those aerosols get trapped under that inversion layer, and they can spread to fields where they're not supposed to go to. Another big issue is with transportation. Fog and frost typically form under nocturnal thermal temperature inversions, and this can cause issues with driving and not being able to see. And another big thing is with pollution, and we see this a lot in areas like Los Angeles and big cities in China, where we get a temperature inversion and those pollutants get trapped under that layer. It can cause a lot of issues for people with respiratory infections and asthma, and it just creates a lot of issues, which is why we need to study these so we can better understand them. The main driver behind nocturnal temperature inversions is the relationship between the soil and the atmosphere above. There are two main factors in this relationship. The first one is land-atmosphere thermal coupling, and this is just a fancy way of saying the energy exchange between the soil and the atmosphere, and it can be influenced by many factors, including the terrain and land cover. The second of these is dynamic coupling, and this is just, again, a fancy way of saying how does the wind influence what is here at the surface. And we can get wind in a lot of different ways. There's just the local gusts, there's a large-scale pressure gradient force, and then from this we get a lot of different interactions between the soil and the atmosphere above. A Kentucky Mesonet station is equipped with 4 thermometers at 4 locations: 0.5 meter, 2 meter, 3 meter, and 9 meter. They also have wind speeds at 2 and 9 meters and wind direction at 10. In order to identify a temperature inversion, 2 criteria have to be met. So the temperature at 3 meters has to be greater than the temperature at 2 meters, and the temperature at 2 meters has to be greater than the temperature at 0.5 meter. Also, the temperature at 9 meters has to be at least 1 degree Celsius greater than the temperature at 0.5 meter at some point during a specified time period. And speaking of those time periods, we looked at 4 different time periods throughout the time between sunset and sunrise the next day. So we have 60 minutes, 30 minutes, 10 minutes, and 0 minutes. And essentially 0 minutes just means that none of the criteria were met at any time during that time between sunset and sunrise. So this is a map of all of our Kentucky Mesonet sites, and it's pretty obvious to see that we have them all across Kentucky. But the 3 that we're going to be focusing on today is Fulton County, Christian County, and Hardin County. These 3 graphs show the 2019 temperature inversion frequency for the 3 stations that we are observing. So we can see that they're very drastic differences despite how close these stations seemed on the larger map. We can see that Fulton County kind of has 2 maximums. Hardin County has a maximum in the fall, but Christian County, on the other hand, really doesn't have a max or a min. It's very uniform across the entire year. So what the colors mean is the blue lines represent inversions, the number of inversions that occur for at least 60 minutes. Red represents the number of inversions for 30 minutes, and then yellow is the same thing for 10 minutes, and then the purple, which are the largest lines, represent inversions that don't happen at all. They last for 0 minutes. So what's interesting to note here is despite how different they may look, they all have maximums in September, and if you remember back to last September, it was very hot, and that's what we consider a flash drought. And so during that flash drought, we had a lot of weak winds, the soils are very dry, and this created a feedback loop that created a lot of prime conditions for temperature inversions to form. And we will look at that later and kind of delve into the mechanics behind that. The first station we're going to look at is Christian County from June 13th, 2019. And this station showed a lot of unique inversion characteristics, and one of those is this 3 pattern sequence of how temperature interacts as the sun decreases. So we first have this period of slower cooling, and as the sun gets low on the horizon, essentially the energy coming from the sun gets less and less, but the energy from the earth increases from hot daytime heating and maximum radiation from the sun during the daytime. Once that hits about 60 to 90 minutes before sunset, we start to see this period of rapid cooling. And this really takes place because we kind of lose that mixing from daytime heating, so we lose that convection at the surface, and we also lose that mixing from increased low level stability due to that radiational cooling, and this actually creates a positive feedback loop between the near surface cooling and the increase in stability, which leads to that rapid loss of mixing, and eventually we get to a point where we cannot mix anymore because the air has become stable, like we explained earlier. And then after we get this rapid cooling phase, about 90 minutes after sunset, we hit another period of slower cooling, and at this point it's really up to what the environment is like at that point, to where we see changes in how temperatures will look. So that'll depend on relative humidity, that'll depend on wind speeds. It's just really up to the environment at this point. Looking at wind direction, we can see that on this night it was primarily out of the north-northwest. But if we look at the colorful elevation map below, we can see there's also a large elevation gradient, also in the north-northwest. But if we look at the picture, which is actually a picture from our camera on the station itself, we can see that the gradient really isn't that large, but more importantly, there's a large group of deciduous trees in that general area. And this is important because when we think back to our wind speeds on the previous slide, we saw that as the night progressed, wind speeds dropped to 0 miles per hour at the station itself. But now that we know that the wind direction was from the north-northwest, from that area of high tree density, we can kind of get a guess at why those wind speeds were so low at the station itself. Because as those winds came in from the north-northwest, they were blocked by these trees, which allowed for the inversion to develop at the station itself with those low wind speeds. Next, we're going to look at a really unique scenario from Hardin County on September 18th, 2019. And if you remember, September was a time of our really hot month. It was a time of our flash drought. And this is going to be interesting because it's going to show a lot of unique characteristics and really highlight how our environment affects temperature inversion development. So if we notice from our temperature graph, we notice this very drastic drop in temperatures. We notice that about 2 hours during that rapid cooling phase that I talked about, we noticed an 18-degree temperature drop. Now this wasn't because a cold front came through or it rained. We were under a high pressure at this point. This was purely just the difference between the daytime heating and the nighttime cooling. It cooled 18 degrees in just about 2 hours. And this is the result of this low heat capacity of the dry soil. The soil was so dry that it was not able to hold that heat, and so it just reflected it and emitted it right back up into the atmosphere. But what's also really important to notice is that about 3 hours after sunset, the inversion weakens, it almost disappears. Something at that point happens to promote a lot of mixing. But why does this happen? So if we look at our topographic map, we see that the winds during the 10-hour period are primarily out of the east-northeast. Also out of the east-northeast is a large group of deciduous trees, like what we saw at Christian County. The short and sweet conclusion to this is simply inversions are highly variable even on a small geographic scale. Looking toward the future and our future work, we're really going to focus on expanding our inversion observations. We're going to start taking more soil samples, we're going to start looking at more complex terrain, and like I've said throughout this whole thing, modeling is a must. We're going to start modeling and start looking at these temperature inversions on a theoretical basis, because understanding inversion development fundamentals are going to help us better forecast these highly variable events. And that's really going to help us mitigate the problems that we're seeing in agriculture, transportation, and pollution. So I hope you've enjoyed watching this video, and thank you for watching, and I hope you've been able to learn something new.